Okay, so the next thing would be to construct some proper entanglement criterion, and that was done with uh, a very simple geometrical criterion. So you remember maybe geometrical spell inequality. So it was so that if you had a vector v and set of vectors s, um, then if I have v for every s belonging uh, to s, if I have v times s equal to greater than s times s. No, I'm sorry, v times v v times s, then v does not belong to set S. Okay, you remember such a thing? Okay, so basically it's a statement saying that if you have a vector outside a convex set, it has some component that sticks out of this set. This set, of course, contains zero. So this time our V will be the correlation tensor um, of a two-qubit state, let's say. So Tij equal to trace rho sigma I sigma j. Okay, and S would be any separable, any tensor product of a separable state. So your entanglement criterion is now sum of I from 1 to 3 T I j Tij squared greater than and this would be a separable state, right? And this inequality is, of course, linear in S. So the maximum will be obtained for some state on the boundary, which is a product state. So now we can have cosinus alpha. Okay, never mind. So A, B, C, T times D, E, F, where A squared plus B squared plus C squared is equal to 1, and D squared plus E squared plus F squared is also equal to 1. Okay, so this would be the greatest element that this T could have in any basis, and we could just write it as E max, because T describes the correlation function E, and the maximal value of all the settings of this correlation tensor gives me the first number in the singular value decomposition of this tensor, so it's the maximal value. Yeah. So I can write my entanglement criterion that sum T squared change is greater than E max. And now, because I have it for singlet states, I can rewrite it I can rewrite it for normalized Stokes operators, right? So now instead of sigma, I'm using Si, which is no, how do I put it? Okay, and I plus minus and I minus and I plus and I minus, where n is the number, n plus minus is the number of photons with a proper polarization. So I can plug it in because it has values between plus and 1 and minus 1. And I can get the forms. And so if I do it like Margaret Reed and Daniel Waltz did it, I would have the elements of the correlation tensor, which now I will describe as theta, is I only diagonal 2 cos squared of k divided by 1 minus 3 cos squared k. Right, so okay, so what happens in t going to infinity? So this is minus 2/3, if I'm not mistaken. 2/3, and yeah, minus 2/3. So if I take 3 of them and square them, it would be 3 times 4 by 9, which is 4/3, okay, which is kind of strange, but never mind. So with the new approach, we have 1/3. So t is 1/3, 1/3 minus 2 log logarithm of ck. Okay, which this term will become irrelevant for large k, and minus c squared, c squared of 2k, I believe. No, not squared. 2k divided by c 4k, okay, minus 1. So this is for the new approach that we introduced in this paper, and you should have also Emacs, which is Emacs is minus 16 logarithm of c squared minus c of 4k minus 12 of 2k of c of 2k 2k doesn't matter, plus 13 just to show you that something was calculated in this paper, divided by 12 s squared 3 plus 3 of 2k. Okay. And here it was like that you had an criterion for read method. It was something like that for Stokes parameter for this ratio parameters and Stokes parameters. That was something like that. Here was Emacs. And the third one was something like that. So of course it detected entanglement for all value of gamma, for all value of k, but there was some place left for other imperfections, for some noise and so on and so on. And here we also did the analysis, what happens if you lose some photons. But it's a very complicated analysis, and what we did, we took n photon sectors of this state, and we assumed that the losses happen individually in these sectors, and we plug them in. And yeah, just to give the outline of that. So for n equal to 1, n equal to 1 critical eta, so critical detection efficiency was 1/3. This is the usual result. For 5 it was 0.222 approximately. For 10 it was 0.164, and for 100 it was 0.036. So we couldn't prove that that the critical efficiency goes to 0 as you increase k, which would be kind of expected because you gain more and more entanglement. But look, I mean, the higher the number of photons in the component, the lower is the critical efficiency. So for high k, the probability distribution will be centered around some value. So the vacuum will not play a big role here, and the low. So it's like a Poissonian distribution kind of, and yeah, it would be centered around some value. So let's say it's centered around 10, so like 5 would be still a reasonable number of photons to expect. And then here it would be 20. So again, on average, this should be like 1.5, 0.5, the critical efficiency. That's why and that's how you argue that since this goes to 0 with number of photons going to infinity, it should be the same for a full bright squeeze vacuum state. So like this is such a hand-waving argument. Okay, and then there was one result we had. Yeah, there were few more results in this direction that we had. Maybe I won't go into that much detail. But the point was that we were able to make this analysis for even more modes of your bright squeeze vacuum, and that was the multi-port paper, which showed in PRR Research Volume 1. And then, so multi-port, yeah, you just use the ratio and you just use the. I can tell about this. No problem. So the problem is that you need to use the concept of mutually unbiased basis, and there's d plus one basis in dimension d, so you have j I, but if you have take a modulus squared of a product with some other state from some other unbiased basis, it should be always if delta if j is the same as j prime, then it's a delta jj prime delta I prime. But if it's not, then 1 minus delta j prime, then this overlap is constant and it's equal to 1 over d, right? So if something happens in one of the bases, you will have no idea what happens in the other bases. And the trick to use it for to obtain these bases for prime dimension is to use Fourier Gauss modes. So like one set of modes is like the computational basis, so it's I, but the other is a j k is equal to, let's say, bjk, not to confuse you, bjk is equal to sum over 1 square root of d for renormalization, sum over some L, omega, which I will give you in a moment, omega L k plus j L squared A L. Right, so this gives you the complete set of mutually unbiased bases if these are the vectors. But of course, for us, we can use the creation operators, and now we have defined the set of mutually unbiased modes. So this omega is, of course, e to I 2 pi over d. And what? And yeah, so J labels the basis and K labels the state in this basis. And you can use such a criterion, which is S Ij sum Sij squared plus S on A side plus Sij on B side. That should be star, so that should be complex conjugate squared, and these correlations would all be equal to 0, but we want to show that they are entangled if they are less than or equal than. Okay, if that was Schmidt operators, so usual Stokes operators, that would be greater or equal, less or equal than n a plus n p, right? Number of times d minus 1 for some reason. So that's your entanglement criterion. If that is violated, then your state is no. If that is satisfied, then your state is entangled. But the problem is that you should have d plus one such bases for every dimension, but you cannot have, we don't know if we can have them for dimensions which are composite numbers, not prime numbers. We know that it's true for d equal to a prime number, for d equal to a power of a prime, but not for composite numbers like 6. And it's a huge open question if the complete set of bases exists or not. So then you should remove something from this expression. But what we did was, again, how do I write? Okay, so I should write sigma here, sorry, because I used S over there, so I use it sum Sij alpha A, sorry, minus plus S star B I Ij Y, okay, no, it's I, sorry. It's there's only one index because I need to sum them over in all the bases. Okay, so this should be less or equal than projection on the non-vacuum part. So 1 minus omega on A, 1 over NA. Projection on the non-vacuum state plus projection on the non-vacuum state 1 over NB and projection on the vacuum state. Right, so for multi-mode bright squeeze vacuum, we used the criterion like that. And again, it was shown that everything is fine, so there is a violation. And then Marek Żukowski mainly concluded that it's a general rule that if you have this description with this Reynolds-Stokes operator or ratio operators, then you could map any correlations of any bright squeeze vacuum to a two-qubit state, which was very convenient because you can straightforward use the entanglement criteria that exist there for analyzing the bright squeeze vacuum. On the way, there was another paper where we studied Hongman visibility with this ratio. So we compared. So the scheme was something like that you had two photons coming out, and you interfere them, and here's the faceplate, which is delayed. So again, I won't be going through the calculations here, but the conclusion was that you can still detect. I mean, you have a wider margin for other errors to detect this non-classical value of this bunching here than for classical approach. I can give you, for the old approach, I can give you just the visibility. So the visibility calculated with this old method was 1 over 2 minus sec sec squared gamma, okay, and visibility mu was sine squared k divided by cos 2k cos 2k 2k plus log sec log sec hyperbolical squared k minus 1. So let's see what's going on here. Yeah, okay, so the point is that for k going to infinity, so they go both to the classical limit of 1 over 2. Here it's obvious because like you have this part is neglectable, this part will be neglectable. Here you have sine hyperbolic squared divided by cos 2k, so it's a bit less intuitive. For vk equal to 0, they both will be equal to 1, no problem there. Yeah, okay, let's note, because this would be equal to 1, and this would be equal to 0, but it goes to 0 with the same ratio as cos to k minus 1, so they are both equal to 1 at k equal to 0, but this one drops much slower, so that was the idea. But the final touch in this whole project was a paper that was written last year by Marek Żukowski and Bianka Woluncewicz and Konrad Schlitzon. Okay, and Conrad, just Conrad. Okay, so his idea, their idea was to ask why do we use this ratio? I mean, these ratios are very uneconomical because there are a lot of eigenvalues which would never contribute to valuation of a Bell inequality uh, or detection of entanglement, and how? Because if you focus on these eigenvalues, eventually, I mean, they could reach only 1/3 and minus 1/3. So they are totally useless. So the idea was to use such a formula 1 over n square root. So like, because if you have a sine function, the square root will make it more like that, more like mm, rectangular wave function. But why don't we stop there? Just go to infinity with that, and the new Stokes operators were just equal to sine sine as sorry n I plus minus n I minus. Okay, so just a sine function. With 0, you can do whatever you like. If you have many enough photons, it won't matter anyhow. And again, it was shown, yeah. For example, it was shown in their paper that that if you focus on the CHSH inequality, its violation behaves something like that. For alt, for these renormalized Stokes parameters, but in case of these new sine parameters, it will behave more like that. So here you have 0.8 89, I guess. Yeah, 80, 88, something like that. This is of course K, and this is of course 0.88, and this is of course 2.16. So we get much better violation, at least for CHSH, and you get, if you go to change inequality, you can still have less settings than for the previous inequality, which is a great progress, and yeah. And that's our goal, to show that this is a highly entangled state, and this seems to be the optimal idea. Okay, so the experimentally, it's a problem that we have too many spatial modes of the bright squeeze vacuum, because, as I said, I mean, we want to use it for cryptography. That was the plan. And if you have your photons mislocated with respect to one another, then that means that they are kind of distinguishable from one another. So for those people, for Masha Chekhova, who ran this experiment, it was important to have like as few spatial modes as possible, and she obtained that in a very nice way. So she had the source of she had BBO, two crystals, which were apparently sources of the collinear emission, and here there was a monochromator, which is like a diffraction grid accompanied by some lenses, and in fact you see only one wavelength. She saw a wavelength with a spread of 1 nanometer.
I'm very sorry, I just want to inform you that John Selby will be 30 minutes late. So
okay.
Don't run away. Wait for him.
Okay.
Thanks so much.
Sure. So down from few thousand spatial modes, they got to 1.1 mode, which was very useful. Also experimentally, some people like Masha, for example, proposed using bright squeeze vacuum for high resolution spectroscopy in both the time and frequency domain, so you can measure these two things precisely. And what else? There was also a teleportation scheme of this. We're using this state, but like that's pretty straightforward if you know the usual teleportation. So okay, that's it for today. Thank you very much. Let's